In this lecture, we're going to be reviewing lines with a focus on equations of lines. And as a starting point, we're going to talk about one of the characteristics of lines that you usually have to find in order to get the equation of a line, and that's the slope. Here's a formal definition. If L is a non-vertical line passing through the distinct points x sub 1, y sub 1, and x sub 2, y sub 2, then the slope m of the line is given by the formula m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Another way to say this is that this is the ratio of the change in y to the change in x. And in math, we often use the Greek letter delta to mean change. So we can write this as delta y over delta x, meaning the change in y over the change in x. Less formally, if you're looking at a graph, it's sometimes helpful to think of slope as the change in the vertical component, which we often call the rise, even though the graph might be falling, divided by the change in the horizontal component, which we call the run. So if you were tracing from one point to another on the graph, the change in the vertical component is the rise, the change in the horizontal component is the run. This is sometimes a convenient way to think of slope. We have to exclude vertical lines from this discussion, and we'll explain why later. But for any non-vertical line, the slope is a critical component of the description of that line. Even just knowing the sign of the slope gives you a decent description of what the line looks like. It tells you its orientation. If a line has a positive slope, then as you move to the right in the graph moves up. Another way to say that is when the slope is positive, as x increases, y increases. If you have a negative slope, then as you move to the right in the graph moves down. So as x increases, y decreases. So the sign of the slope gives you an idea of the way that the graph points. And the larger the magnitude of the slope, the steeper the slope is. Now this covers positive slopes and negative slopes. Of course, in between the positive and negative numbers is 0. And when the slope is 0, the line is horizontal. You can actually find the slope of a horizontal line following the formula. But if you think of it graphically and interpret the slope to be rise over run, well, this graph doesn't rise at all. Its rise is 0 because vertically it doesn't change. And so the slope of this line would be 0 over the run, and as long as you choose a non-zero run, you're going to get 0. So horizontal lines have a slope of 0. The equation of a horizontal line is y equals b. The y-coordinate of every point on a horizontal line is exactly the same. That's the defining characteristic of the equation. X can be anything, but y is required to be b. And so the equation of a horizontal line is y equals b. So we've covered positive slopes, negative slopes, zero slope. It looks like we've covered every possible orientation. But if you look at our lines, you'll notice that there's one direction we haven't considered. We've considered moving up as you go to the right. We've considered moving down as you go to the right. We've considered horizontal lines. But of course, there are also vertical lines, which we mentioned before we had to leave out of the slope discussion. And that's because vertical lines have an undefined slope. Again, thinking of it in terms of the geometrical interpretation, rise over run. By run, we mean the change in the horizontal component. Well, the vertical line doesn't move horizontally. It moves vertically, and it has no horizontal change, and therefore, the run in this formula is 0. So that's division by 0, which is undefined. You may have been taught instead to say no slope. That's okay. We say that vertical lines have an undefined slope or no slope. As such, you can't use the slope in any way to come up with the equation. You just have to be familiar with the idea that in a vertical line, all of the x-coordinates are the same. The y-coordinates can be anything, but the x-coordinate remains exactly the same. In this example, we've called the x-coordinate a, and so the equation would be x equals a. So these are special cases. A horizontal line has the same y-coordinate the entire time, so the equation is just y equals the common y-coordinate. In this example, I called it b. In a vertical line, the x-coordinate is always the same, and so the equation of a vertical line is x equals a, where a is the common x-coordinate. So we have simple equations for horizontal lines and vertical lines. For slanted lines, it's a little bit more complicated. You have to take into account the slope, but you also have to take into account what points that line goes through. Two lines can have the same slope but go through different points. Then you've got to put a little more work into it, and there are actually a few different ways that you can write the equations. I'm going to show you the two most common. I'm going to start with point-slope form. To come up with the point-slope form of the equation of a line, you need to know a point on the line and the slope. An equation for the line through the point x sub 1, y sub 1 with slope m is y minus y1 equals m times the quantity x minus x1. Now we can write the equation of a line in another form that isn't the point-slope form, and we're going to get to that one later. And it tends to be more popular, but I'm not sure why, because there's a logic to this one. This one comes from the slope formula. Let me remind you that to find the slope of a line, we do y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That gives us the slope. Let me erase those subscript 2's and rewrite this equation so it's not written as a fraction. To do that, I would multiply both sides by x minus x1. So I would wind up with y minus y1 equals m times the quantity x minus x1. There's the point-slope form. The point-slope form of the equation of a line is just a rewrite of the slope formula. If you can remember the slope formula, then you can remember the point-slope form of the equation of a line because they're essentially the same thing. We drop a couple of subscripts and we get rid of the fraction look, but otherwise it's the same. And the point-slope form is convenient because you just need to know any point on the line. When we get to that second version that people seem to like better, you'll notice that it asks for a very specific point on the line. And if you don't know that, then it's harder to use in my opinion. Let's find the equation of a line using the point-slope form. This example says find an equation of the line through the points negative 3, 7 and 1, 6. Let's sketch what this line would look like. We're not going to draw any of the tick marks, just a quick idea. Negative 3, 7 would be in quadrant 2. 1, 6 would be in quadrant 1, and it would be a little bit lower. So we get this line that slants downward. When we go to find the equation of this line, we better wind up with a negative slope, because we can see in the picture that the line has a negative slope based on its orientation. It's also a very shallow line, so its slope should have a small magnitude. Okay, back to the problem. We're trying to find an equation of this line. Let's use the point-slope form to do that. We said that point-slope form is just a rewrite of the slope formula. Y minus y1 equals m times the quantity x minus x1. We need to know a point on the line. Well, we have two options there. That's not an issue. We also need to know the slope. And that's where we're going to have to start doing some math here. We need to find the slope. We said that the slope is the change in y over the change in x. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. It does not matter which point you call x1, y1 and which point you call x2, y2. All that matters is that you stay consistent when you subtract. Whichever point you use first in the numerator, you must use that x-coordinate first in the denominator. So I'm going to do this in the standard way where I call this x1, y1 and this x2, y2. But it doesn't matter, you'll get the same slope either way. So if I use that labeling, then y2 minus y1 would be 6 minus 7, and x2 minus x1 would be 1 minus negative 3. 6 minus 7 is negative 1, 1 minus negative 3 is 4, and we get a slope of negative 1, 4. Notice that that fits with our graph. We got a negative slope, just like we anticipated. We got a slope with a small magnitude because the line is shallow. It's not a steep line. Now we can use either point to come up with the equation of the line. This is sometimes confusing because we labeled this as x1, y1, and it looks like we have to use that point in the formula. That's not true. There are actually two different ways that we can write this, which is why it says find an equation of the line and not the equation, because there are actually infinitely many equations. We have two obvious ones. We could actually use the first point and write this as y minus 7 equals negative 1/4 times x minus negative 3, which becomes x plus 3. That's one possible answer. We could also write y minus the y-coordinate of the second point equals the slope, negative 1/4, times x minus the x-coordinate of that. One way to show that both of these equations work is to take the point that you didn't use and show that it satisfies the equation. So we could take the point 1, 6 and plug it into this equation, and you'd see that you get a true statement. You could take the point negative 3, 7 and plug it into the second equation and also show that you get a true statement. There's another way that we could rewrite these to show that they're the same, and that's to solve them both for y. And when you have the equation written in the form y equals the slope times x plus a number, we call that the slope-intercept form, and that's another form of the equation. An equation of the line with slope m and y-intercept 0, b is y equals mx plus b. And it's a nice clean form. It doesn't look as ugly as the point slope form does. But there's a major restriction. You have to know what the y-intercept is in order to use this. Whether it's given or you deduce it, you have to know what the y-intercept is. Let's do an example where we have the y-intercept just to show you how nice it is in this case. Let's find the slope-intercept form of the equation of the line passing through the points 0, -6, and -3, -2. So the slope-intercept form is the form y equals mx plus b. In this example, we know what b is because we have the y-intercept. The y-intercept is 0, -6, so the value of b is -6. Notice we couldn't do that right away in the previous example because we weren't given the y-intercept. There is a way to deduce what it is without using point-slope form, but in my opinion, it's just easier to use point-slope form. Here I'm given the y-intercept, so why not use it? The slope-intercept form is nice when you have the y-intercept. We don't have the slope, but we know how to find it. Pause the video and see if you can come up with the slope. And it doesn't matter which point you call x1, y1, and which point you call x2, y2. And in fact, I have a general rule where I try to make sure that my denominator is positive. So I would subtract these in the opposite order from what most people would do. I would call the first point x2, y2, and the second point x1, y1, and do -6 minus -2. And since I use the -6 first in the numerator, I have to use its x-coordinate first in the denominator. So it would be 0 minus -3. And I get -4 divided by 3. So my slope is -4/3. Now I have the slope and I have the y-intercept, so I can jump straight to the slope-intercept form of the equation of the line. All right, y equals -4/3 x minus 6. You could write plus -6, that simplifies to -6. You can verify that this is the right equation by taking the point that wasn't the y-intercept and verifying that it satisfies the equation. You'll see that it does. So these are the standard problems where you're given points on the line and you're asked to find the equation of the line. A lot of textbooks will include geometry style questions. Let me remind you of a couple of facts. Two non-vertical lines are parallel if and only if they have the same slope. We have to exclude the vertical lines from this statement because they don't have slopes. So vertical lines are parallel to one another, and then non-vertical lines are parallel to one another if they have the same slope, and if two lines have the same slope, then they're parallel. That's a pretty easy rule, and as such, I'm not going to do an example that uses that. You can practice those on your own. There's a second geometrical rule involving slopes that I do want to demonstrate because it's a little more complicated. Two lines with slopes m1 and m2 are perpendicular if and only if the product of their slopes is -1. Another way to say that is that the slopes are opposite reciprocals of one another. They're not literally reciprocals of one another because if two numbers are reciprocals, their product is +1. So we say they are opposite reciprocals. They have different signs. Notice that we specified that both lines have slopes, so we're ignoring vertical lines. The rule for vertical lines is easy. Vertical lines are perpendicular to horizontal lines, and horizontal lines are perpendicular to vertical lines. But if you have two lines with slopes, the only way they can be perpendicular is if the product of their slopes is -1. In other words, that their slopes are opposite reciprocals. There are some applications where we have to find the equation of a line that's normal to a curve, which means that it's perpendicular to the tangent line of the curve. So these come up from time to time, and as such, I want to demonstrate an example of this. The example says, find an equation of the line passing through the point 6,1 and perpendicular to the line y equals -2/3 x plus 3. Let me draw a quick sketch of what's going on here. I'm not going to try to make it perfect, just to give you an idea of what's going on. The given line has a y-intercept of 0, 3, so it's going to cross the y-axis somewhere above the x-axis, and it has a shallow negative slope, so something like this. The point 6,1 lives somewhere above that line. You can show that that's true. And we're saying that there's some line that's perpendicular to the given line that passes through there. So this dashed line makes a right angle. We are to find the equation of that dashed line. Now you can see that it has a positive slope. That part's obvious. What's not as obvious is what the actual magnitude of the slope is, but that's where the rule comes in. The rule says that the slopes have to be opposite reciprocals. Since the slope of the given line is -2/3, the slope of our line is 3/2. If you have the slope of one line and you want to find the slope of a perpendicular line, you take the opposite of the reciprocal of the slope of the given line. Okay, so now we can find the equation of our line. Notice that we can't jump straight to slope-intercept form because we don't have the y-intercept. And again, I know we could solve for b. I know some of you learned a technique for doing that. But it doesn't specify that I need to write this in y equals mx plus b form. It just says find an equation. I'm going to use the point-slope form. Y minus the y-coordinate of our given point equals the slope of our line, 3/2, times the quantity x minus 6. I'm not doing an example of parallel lines in this video, but let me quickly explain. If our line had been parallel to the given line, then the slopes would have been the same. Rather than taking the opposite reciprocal, we would have just used the slope negative 2/3. Let's end the video with a couple of word problems. We're still going to be finding equations of lines, but now we're going to have to extract the information from a story problem instead of just being given the raw facts. Let me give you an example. A baby weighs 10 pounds at birth, and 3 years later the child's weight is 30 pounds. Assume that the weight W is linearly related to the age T. Express W in terms of T. Let's start with that last sentence. What does it mean to express W in terms of T? We're being asked to write an equation of the form W equals some expression, and in that expression the variable is T. We have to come up with that. Now what I'm going to do is show you an organized procedure for coming up with this equation. You might be able to guess at it, but I'll tell you that a lot of people who have tried this on exams without showing their work have guessed wrong. They look at this and they say, well, after 3 years the child's weight is 30 pounds, so isn't that just W equals 10 times the age? And the answer is no, because that doesn't give us the right weight at birth. Notice that at birth time would be 0, and this model would be predicting that the baby weighs 0 pounds at birth. That doesn't fit with the information we were given. So we're not going to just guess at it. We're going to come up with an equation of a line using the same steps that we did before. What we're going to do is interpret the information as ordered pairs, and then we'll use our rules for coming up with the equation of a line in order to get the relationship between W and T. Notice that we're using W kind of as the output. It's in the same place as Y might be. And we're using T kind of like the input. The weight is the dependent variable and the age is the independent variable. So when we write our ordered pairs, we're going to write them in the form T comma W. Time is being used as the input variable, weight is being used as the output variable. So we're going to write our points as T comma W. Let's see what information we were given. The baby weighs 10 pounds at birth. So I can interpret that as a specific point. At age 0, at birth, the weight of the baby was 10 pounds. Then we're given some more information. 3 years later, the child's weight is 30 pounds. After 3 years, the weight is 30 pounds. Now I have two ordered pairs. We know how to find the equation of a line given two ordered pairs. We just find the slopes. I would do 30 minus 10 over 3 minus 0. 30 minus 10 is 20. 3 minus 0 is 3. So our slope is 20/3. I can jump straight to the slope-intercept form. Now you want to stop yourself from writing y equals, because remember we called the variables t and w. We're using w like we would normally use y, so we're going to write w equals, remember that's exactly what we were trying to do by the way, the slope times, I know you want to write x here, but remember the variable is t plus 10. This is the correct formula for our scenario. Not w equals 10t. Notice that if I plug 0 in for t now, I get 10. And if I plug 3 in for t, the 3's would cancel and I get 20 plus 10 is 30. Let's try another example, and I chose this example because I would not do it in the same way. It's got different information. It says a college student receives an interest-free loan of $8,250. The student will repay $125 per month. Express the amount P remaining to be paid in terms of the time T, where T is measured in months, so that the first payment corresponds to T equals 1. Now, why would I do this problem differently? Well, it's because we were given different information. Here we were given one pair between the two variables. We know at time 0, at the beginning, the amount remaining to be paid was $8,250. So we could pair those two numbers, and we'll talk about what order we would pair them in a moment. But the $125 isn't paired with an amount of time. It's a ratio. It's an amount of money per month. That sounds like a slope. So in this example, we're not going to have to find the slope. We already know the slope, it's given. The one thing we have to be careful about is which variable we're using like y and which variable we're using like x. Notice that the problem says express the amount p remaining to be paid in terms of t. So our final answer is going to be an equation of the form p equals some expression with variable t. So when we write our ordered pair, we're going to write it in the form t comma p. And when we write our slope, we want it to be the change in p over the change in t. The change in the second coordinate over the change in the first coordinate. Let's see what information we were given. A college student receives an interest-free loan of $8,250. At time 0, the amount that needs to be paid back is the entire loan amount, $8,250. So the point we were given is 0, 8,250. Now, one way we could proceed is to pick a certain amount of time in the future and figure out what the balance would be at that time. But there's a slicker way to do this. That's the change in money over the change in time. That's exactly what our slope is supposed to be. However, this is a slight mistake. We don't want to write that m equals $125 because that would increase the balance. Remember that the student is paying off the loan, and the slope represents a decrease in the balance, so the slope is negative 125. I have the slope, I have the point whose first coordinate is 0. I can jump straight to the slope-intercept form. I know you're going to want to write y, but remember that we're using p as the output variable here. P, the amount remaining to be paid, is the slope times the input variable, which is t, plus 8,250. Notice that this will work. If I plug in 0, it gives us the initial balance. And if you plug in 1, that will subtract one payment of $125, leaving a balance of $8,125. If you plug in 2, it will subtract two payments of $125, a total of $250, leaving a balance of $8,000, and so on. A lot of people can come up with this equation without having to think of it in terms of these nerdy rules. I can see a lot of people jumping straight to the answer by just saying, well, I'm starting with $8,250 and I'm subtracting $125 as each month goes by and coming up with the equation in this format. And there's nothing that says that we have to write the equation in a specific way, so this would be a perfectly fine answer. Okay, that ends our review of equations of lines. If you have any questions for me, come find me in an office hour or shoot me an email.